Okay, now it's time to give an example for the bisection algorithm. And our main application here is finding the finding the yield, sorry, of a bond. Okay, and for this purpose, we will introduce some example. And in our example here, you can see some of the bond parameters are already given. So suppose that you have a bond with maturity in 2 years. Face value is $100, as we can see. Annual coupon rate is 4%, that which is paid semi-annually. So that means every 6 months we are going to receive $2 coupon payment. And the market price of this bond is given as $95. So basically the bond price, here finding the yield of this bond means we are trying to find the discount rate y that when we apply to the right hand side of this equation to find the present value of this cash flow gives us the market price of the bond. And basically you can subtract this market price and your function becomes this f of y. It's a function of the yield of the bond, and we are trying to find the root of this function f of y. So basically this is our setup, and if we look at our sample code here, we can try to implement this in Matlab. So for this problem, let's go to our bisection here. So you can see first I need to set up the times of each payment. Okay, so you can notice that I have my regular coupon payments every 6 months, and the maturity is 2 years. So the first vector I write is the vector of payment times. That's for the cash flow date. And then we have the coupon payments, which are going to be $2 every 6 months. So this is how much I'm going to receive. And then we have the market price of the bond, the face value of the bond. And what I need is to define now a function that will give me the present value of this cash flow. Okay, so you can notice that I have all the payments from the coupons, and these are discounted. So we have this vectorized multiplication. So each date we multiply with the yield, and we have the coupon payments. We sum all the coupon payments, and plus we also need to sum the last payment, which is the face value of the bond as well. So if we add these two together, we get what's the basically present value of this cash flow. And as an example, you can evaluate this at some particular values for the yield. So you can evaluate this part to see if everything is working. So if this is fine, then the next part is now to implement the bisection algorithm. So in order to do that, basically we can start with a relatively large interval for finding the possible yield value. So you can make this interval larger or smaller depending on the initial sign that you get. For example, if we get different signs from our function, then that means there is a root in this interval. So you can check this basically at the beginning of your bisection algorithm. So if the signs are the same, that means there is no root in this interval. So you need to change your initial a and b in order to get a result. And you can notice that I'm also evaluating my, obviously, the function. So here we have the bond price minus the market price, because we want to make this quantity equal to 0 or as close as possible to 0. And also I also need to introduce actually a few extra parameters. So this m here is going to define what's the maximum number of iterations I want to continue taking the half points of these intervals. So I set this equal to 20. And then I need to introduce some tolerance levels for my stopping criteria. So you can see that we need to also check whether a convergence or stopping criteria is satisfied or not. And in this case, you can see the absolute value of E, so which is corresponding to the length of this interval. Okay, so that's the length of interval. So if the length of this interval is already too small, then we can stop as one possible criteria. And another one is basically if this W, which is which is actually your functions evaluated at this particular midpoint C. If the function is already very close to 0, again, this can be considered as a stopping condition. So we are already very close to satisfying the root problem. That means we can stop and return whatever we get for this value C as the yield from our algorithm. So you can run this algorithm, and basically you can check whether your stopping criteria is satisfied or not. If necessary, you can increase the number of iterations if it is taking longer to satisfy these stopping criteria. And also, actually, it's good maybe to put a flag. So for example, you can set the flag equals to 0, and this condition is satisfied. You can set the flag equals to 1, and at the end here we can also print out what's the latest value of the flag, and we can check whether the stopping criteria is achieved or not. If the stopping criteria actually if not achieved, and if flag is still 0, then we can actually increase the number of iterations in this for loop. So we can test this piece of code. Let's run it all, and let's see if we can get the yield of this bond. So we can see that we have the flag equals to 1. That shows that our bisection algorithm actually converges successfully, satisfying one of those stopping criteria. And the yield that we got is actually around 6.6%. And you can see that the price that we get by evaluating our cash flow with this yield actually is very close, 94.98, which in this case, in this example, we have the market price equals to $95. So actually this is the yield of this bond, because we can see we almost get the same market price once we apply this yield for the cash flow. So this shows that basically we can use the bisection algorithm, as we demonstrated here, to find the yield of a bond. In the later examples, we will see how to use the bisection or the Newton's algorithm to find the implied volatility of an option. So that's going to be another example we will consider. Thank you.